Now, in the last video, we were talking about Niels Bohr quantum model for the atom, and we explained the basic things you need to know. And then I got into a little bit of detail, but remember this: all atoms have 7 main energy levels or shells, which go from K through Q, or from 1 through 7. Each of those cells will have several subshells, just as many as the number of that level. So, for example, level 5 will have as many as 5 subshells. Within each subshell, electrons are organized into orbitals. And all the first subshells can only put 2 electrons inside of them. All the second subshells can only put 6. All the third subshells can only put 10. And if you get to the fourth subshell, you can only put 14. Always remember also that means that the level 1 will take 2 electrons, level 2 will take up to 8 electrons, level 3 will take up to 18, level 4 will take up to 32, and so forth. But in actual nature, you never will find any atoms that will actually occupy the 5th subshell of level 5 on its ground state, which means these particular orbitals here, or subshells, will never be occupied by any atom in nature, because no atoms that we have found or yet isolated are that large that they will actually need that much space for the electrons to be at. Okay? So remember, 7 main energy cells with several subshells each. Within each subshell, the electrons are organized into orbitals, 2 electrons per orbital, because one spins upwards, one spins downwards. Electrons can stay in the lower possible energy level available, which makes them fill in the shells in this order. Alright? 2 electrons will never be able to be in the same quantum state as another electron, since they're going to be fermions made of matter that must obey the principle that 2 objects cannot be in the same time in the same space. And also remember that means that they're going to try to avoid each other as much as possible, especially since they both have negatively charged and they're going to be repelling each other. Okay? Also remember that we talked about that it will take more energy for an electron to be at a higher state or far from the nucleus than to be close to the nucleus and still be within the nucleus. And if you excite the electron enough, it will go out higher and higher until eventually leaves the atom altogether, which is exactly what happens when atom reaches this plasma state. The electrons get so much kinetic energy that they just fly out of the atom because they get so far from the electromagnetic force that actually attracts them to the nucleus of the atom. Now, the interesting thing about what we just talked about then is that there are these empty shells or space for them to be at, but the electrons never quite go there unless they get excited, in which case they will jump from wherever they are to one of the available empty shells. Okay, and now we'll talk about how that works in a second. But remember this first. Energy can only be transferred into smaller and smaller chunks until eventually it can get smaller than that. Because we talked about in the quantum physics chapter that the energy, electromagnetic energy or light, is transmitted into small packets of energy called quanta, and each of these quanta is equivalent to whatever one photon can actually carry. And so the photon is the particle of light, right? Or whenever you think of light as a particle, because you can also think of it as a wave. It's got the whole thing that sometimes it acts as a particle, sometimes it acts as a wave. It's one and the same at the same time. But when light is hitting an object, it's really a photon also that's hitting these objects. And each photon carries a specific amount of energy. It's like they have just enough energy cache. Now, if one of these photons hits an electron, and that's what this picture on the top left is showing you here, then this electron gets excited. And if it gets excited, it gets more energy, starts spinning around faster. And if it spins around faster, it will jump to a higher level of the nucleus. Now, the higher energy state will require so much energy that eventually the electron will return back to its normal state, and as it does so, it will emit the light that it had absorbed, and so it will emit a light proton. By the way, the same thing can happen if the electron gets hit by something, another electron or any other particle. It doesn't have to be light that hits the electron. Anything that hits the electron and gives it a little more oomph, it will create this effect where the electron will jump up, and eventually, as it jumps back down, it will have to release the energy because it's going to a lower state of energy. Just like when you go from gas to liquid, you release energy. And so then it will release this packet of energy as a light particle. Now remember that if you actually look at the energy levels of the atom, the way it works is that as you go higher and higher, the energy amount will increase more and more. But remember that sometimes the 4s layer of the next shell is actually lower in energy than the higher layer, the higher subshell of the previous shell. And that's because it's really hard to put electrons in the d orbitals. And so it's going to be easier for the electron to be in the 4s circular orbital than in the 3d orbitals that you saw before, which are very, very strange in shape. So what that means is that as you go higher and higher, the electrons will try to assume this sequence, which is what we talked about in the previous video. Okay, but if the electrons jump around between these orbitals, for example, if I go from the 2 all the way to the p, or back from the p all the way to the 2, this is how much energy I will have to either absorb or release. And depending on how much energy I absorb or release, it's going to have a different intensity or a different frequency, which also means a different wavelength. And if you have a different wavelength, it has a different color. In other words, when an electron jumps back all the way from the outside to the inner layer, it's going to release a lot of energy. And that's violet, you know, close to ultraviolet. If it releases a little lower than that, it's going to release something like, you know, more greenish, lower than that bluish, lower than that yellowish. And so the bigger the jump in energy, the more close to violet this color is going to be. The smaller the jump, the closer to red it's going to be. And just like the power of stars, the red is the weakest and the violet is the strongest. It has to do everything with light, right? What that means then is that you can tell how far an electron jumped by how much light or what color light is being emitted by the electron as it jumps back into the layer that it belongs to. And remember, this is going to depend on how far the jump was as it goes back to what's called its ground state, or the layer that it's normally at. Now, because different elements will have different shells occupied, how much they jump up and down will be different for different elements. For example, over here you have uranium. If this electron right here wants to jump, it's only going to jump all the way up here. That's a big, big jump. And so when it jumps back, it's going to emit a color that's going to be close to like violet or something. Maybe even more than that, like ultraviolet or gamma rays. Because of the energy that's being released to it, it is that strong. But an atom that's smaller will make smaller jumps because it will have available shells closer to wherever the ground state of the electron that's jumping actually was. Which means different electrons will absorb and release different colors of light. Because you see, in order for this electron here to jump all the way up there, it's going to absorb a lot of light. It can't absorb just a little bit. Because if it absorbs just a little bit, it will have to jump just a little bit. But it can't jump just a little bit because all of those shells are occupied. So it can only jump a lot. And therefore, when it jumps backwards to the ground state, it can only release a lot. This means that each atom has a specific absorption spectrum and a specific emission spectrum. Which means if you look at the color of the light that's emitted by an atom that's actually absorbing and releasing energy, it's going to be different. So look, for example, hydrogen will release energy or absorb energy in these particular wavelengths. But helium will absorb energy in these particular wavelengths. Mercury will do these. Uranium will do all of these. And so if you get an atom, any atom of your choice, and you put it through a device that makes the element actually shine or be exposed to electricity, and we call that a cathode ray tube. And especially if it's in a gaseous state, okay? And then the light will shine through this and will go through a slit. It will split the atom apart. We actually did this in class. It's called the spectrophotometer, right? You will see the bands forming from the light that comes from this element. Now, some elements will make some kinds of spectrums. Other elements will make other kinds of spectrums because of how much energy it can absorb or release depending on which orbitals are available or taken by the element, depending on what kinds of jumps this element can make. For example, the reason why uranium can do so many jumps is because it has so many layers that it can jump from many different places. And so, for example, let's go back to that uranium drawing that we were looking at before. So you see, it can have this electron jump a little bit up there, but it can also have this electron jump here, it can have this electron jump there, or that electron jump all the way over there, that electron jump over here. So since it can make so many different jumps, it can absorb a lot of different kinds of light and also emit a lot of different kinds of light. But since hydrogen only has a few electrons and a few available shells after that, it won't jump with as much power as the other ones were, or as much variety as the other ones did. And that means that you can identify elements based on their absorption spectrum or on their release spectrum. Absorption will be the opposite of this. You would have all the colors, and you will see which ones are missing. And the emission is the one you see here, where you see only the ones that's being released from the atom. And a really cool thing we do in chemistry class is that you can do a flame test. When you actually burn that element and you realize that certain elements burn with different colors because they absorb and release different amounts of energy. And that's really cool. And what this means basically then is that you can use the energy that can be absorbed by an element to actually determine what kind of element you're talking about. And actually, other scientists actually discover that if you expose these atoms to electromagnetic fields, you can call what is called Stark or Zeeman effects, where you shift the spectrum of the element. Think about it this way: the orbitals are lined up in a specific location, all those little shells. But if you put a magnet near the actual atom, it's going to make the whole cloud shift a bit. And that means it's going to shift the spectrum that you expect to see from that element. And so you're going to create what's called the Stark effect. You can say it can do the same thing through electricity, not through a magnet, and to do something that's called the Zeeman effect. So in other words, whenever you see a change in the spectrum that you expect to see out of hydrogen because of a magnet, that's called the Stark effect. Whenever you see a change in the spectrum you expect to see because of an electrical current, that's called the Zeeman effect. Alright? But remember the following things about this, because this is all you need to know about this particular batch of videos. Atoms have 7 main energy levels or shells, which go from K to Q, or 1 through 7. Each of those shells have subshells, which have many, many layers of energy. Within each subshell, you will have orbitals where the electrons will be in pairs, one spinning upwards, one spinning downwards. Electrons will stay in the lower possible energy level, which is called their ground state. And they will avoid staying where other electrons already are, which will give them a specific order on how they fill the layers of the atom. And they can only absorb certain amounts of energy, and that there's a minimal to how much energy can be absorbed that's called or transmitted, that's called the quanta, or a photon, or however much one photon can carry. And since different elements have different electron compositions in their cloud, you're going to have a different spectrum for the absorption and release of energy as electrons jump up and down the layers, absorbing and releasing energy, which with different intensities means different colors. And this spectrum can be shifted in the presence of an electromagnetic field to create. But in a normal situation, each atom has a specific field, which means you can actually use the spectrum to determine what element you're looking at, just like you do in the flame test in chemistry class. Alright? Alright, so I'll see you guys in the next video where we're actually going to make sense of why we care about this stuff.